Okay. Why don't we get started? If we could. Yes. All right, I'm going to have to find something to hold this with in the future, but for the moment, I will try to keep it more or less the same distance from my mouth. So, welcome. My name is Paul Hilfinger. I'm with Electrical Engineering and Computer Sciences, and this is Programming Languages and Compilers. This is not the spring of 2010. It is the spring of 2011. For those of you who are signed up for this for the spring 2010 course, I'm afraid you'll have to travel back in time for a year. All right. Yes. Well, all right. Let's see what's going on here. Is that any better? Yeah. Okay. All right. This class is supposedly being screencast. That is to say that is being broadcast somewhere or recorded, and this audio is also being recorded. That's at least is supposedly what's happening. Whether this is actually happening, I don't know. I'm sure you will let me know. All right, so I have been, over the last several years, I've been trying to move this course into, and lots of us have been trying to move our courses into more online versions. So this time, all of the materials that you need, texts and everything else, are available online. In particular, there is a page, if you go to the class web page, which is at the usual place, www.inst berkeley edu//CS164, you will find various information about a page of information about this course that you should definitely read. I will have a few items that I include in this lecture, but basically you're responsible for reading it. This semester we're doing something a little different. We're experimenting with this little startup company's product called Piazza, it's 3 Z's, which is basically a discussion group type thing in lieu of B spaces, whatever they are, groups or news groups. And this is supposedly a wiki style, this is not supposedly, this is a wiki style accumulation of notes that both the staff and students can modify. It's been our experience in the past that you guys, among you, have quite a bit of expertise that you're only too willing to share with your fellow students, and this is good. So we'll take advantage of that. And I hope we'll see how it works out. Please, we are evaluating this. I think Dan Garcia has got at least one section of something that he's doing with it, and it would be nice to have some evaluation of how this works out. So my TAs are at this very moment handing out, or were handing out, class account forms. You can make sure that you get one before the end of the week. And on Friday, there will be a little, we'll be asking you to log in and all that sort of business. You can log in already. I noticed that some people have already, in fact, signed up for the for Piazza, for the discussion group. Also, another thing you should know about, and is that this is a course. The projects in this course are partnership projects. They are required to be partnership projects. As I know, there are hotshots among you, and I will be keeping my eye out for you, but I will not allow you to work alone. You must share your expertise with your fellow students, and in the process, learn to get along with people whose skills are so inferior to your own, since you will be required to do that in the real world for the most part. And I have a little reading assignment here. These are online notes. I believe they are, in fact, I know they are posted now. You should be able to find them. Okay, so it is every instructor's wish that students read the material before the course begins or before the thing is presented. So I'll just present this wish. I know perfectly well that some of you, a few, maybe 40 or 50, will not actually do this, but that's okay. I mean, we understand that. Regular homework is not as seriously graded as projects. It's in fact, we look to see whether you've done it. It's mostly finger exercises to get you to try to understand the material better. It's mostly for your benefit, not for purposes of our own evaluation of you. It's the projects that are the important programming assignments. More on those later. And everything we do this semester will be electronic. So in particular, this gives you a chance to learn, if you have not already done so, something about the industry, not industry standard, but the practice of using source code control to keep versions of your software around. We'll be talking also about that. Now, we are using as the target language for the project some dialect of Python, and we're going to be implementing it in C++, and there are various online materials, as it says here. Yes, that's right. The target is Python, which we have never taught you. The implementation language is C++, which we have never taught you. We are going to have you're going to be using a bunch of tools for helping to build the project, which we have never taught you. And furthermore, I don't propose to spend lecture time teaching you most of this stuff. Welcome to the real world. Basically, I think that by this time you've learned a programming language. And so I'm quite serious that I expect at this point that people can, now that you understand what programming languages look like, we can perhaps pick them up a little faster than you did in the past. And also, you don't have to be anchored. And also, I really want to get you people so that they leave not anchored to the seminar lecture kind of way of learning things, but can actually learn things on their own. So those are the reasons. Now, let's be honest, okay? I mean, I am Paul HILFINGER. If you have not heard of my reputation, ask your friends about me. You know, wasn't that what Vito Corleone said in the second Godfather thing? Ask your friends what I'm like. And so ask your friends about me, right? You can expect these very hard projects that people will work along on. And as you see, we're expecting you to learn programming languages that we haven't taught you before. Many of you will think, perhaps, or some of you may think that this is unfair, that I am an ogre, and that this is really terrible. I should explain. All right. Perhaps some of you saw the 60 Minutes profile some years back of Michael Phelps. Anyone see that? See that one? Well, they did a profile of him after he won the Summer Olympics, after he got 8 gold medals in the Summer Olympics swimming. And in this profile, they featured his coach, a fellow by the name of Bob Bowman, I think his name is, who they said got the nickname the Mad Scientist because of the workouts that he had his swimmers do for him. He gave an example, 10,000 meters for time. Now, those of you who are swimmers know that this is quite an experience. For an Olympic class swimmer, this is about 2.5 hours of all-out swimming. And Phelps commented on this. He said these workouts were horrible. You looked at them on paper and you said, that's impossible, I can't do that. But by making us do it, he gave us the confidence that we could do anything we put our minds to, and that is my ambition. That's why I'm doing all of this to you. I want you to know now, just keep this in mind while you're despairing in front of the terminal. This is what I'm doing. I intend for you to walk or crawl, as the case may be, out of this course with the firm and completely justified conviction that you can program anything. Right? That's my ambition, and we'll see how that works. So let me know how that works out. Oh, for heaven's sakes. I really got to remember to reset the settings here. So my so in summary, sort of my generic advice, DBC and RTFM. DBC means don't be clueless. In other words, don't allow yourself to be mystified by anything that you encounter. Find out what's going on. Understand what you're working with. Understand your tools. Understand the material. Don't allow yourself to treat these. Don't be the sorcerer's apprentice who just says these magic words, not understanding what they mean. But do try to avail yourselves of all the resources that written resources that we provide you and that are on the web, and understand what's going on. And of course, what goes with that is RTFM, which all of you know means. Which means read the manual. And we have material for you. We do hope that you read it, and you will actually find it useful. It's not just blather. I am required to do this. Well, I'm actually not required to do this, but I should do it. Just to warn you, we do treat plagiarism seriously, and I should warn you in addition, I happen to be a member of the Student Conduct Committee. In fact, I have an academic dishonesty case just next week, as a matter of fact. So, I'm probably not the right person to cross on this particular subject. Okay, I hope that that's all of the unpleasant stuff that I have to do this year. All right, so about the projects. The hidden agenda, this course is called Programming Languages and Compilers. And you might think, oh, well, that means it's about programming the languages and compilers. Well, not really. Yes, we do that, sort of as a cover, if you will. The real purpose of this course, however, is to get you experience in actually doing a substantial project. The project is in modules. There are extensive specifications for parts of it that you will have to meet. You can't just make up what you're supposed to do. It has to conform to what we ask for. The output has to conform to what we ask for. There are pieces that you have to start working with, and they are complicated. You have to master them. You have to work with your teammates in some effective way. We'll expect you to do testing and all the other good things that that one does one is supposed to do in the real world. Although we might name certain software companies where we doubt that they do it. You get to use these various tools that I talked about, like version control, and you get to learn a language that some of you perhaps have not studied before. So the general rule here will be to start early, get to know your partners, set up regular meeting times, whether you need them or not, and I will be checking back with you. We'll be doing some team dynamic sorts of checking on you to make sure that things are going well. Again, this is an important part of the course, so please treat it seriously and take a serious consideration of who your partners are going to be. Okay, enough with the administrivia. Let's start doing some actual introduction to the actual material of this course. The general, and I should say, by the way, I do have office hours. I've posted them. You can come around and talk to me. The TAs will be posting their office hours. You can talk to them. You can send us email. And I strongly urge you, please don't. Some students get it into their heads that the professors get annoyed when they are bothered with student questions. We may very well be annoyed, but on the other hand, you are paying our salaries, or part of them, so you're supposed to be able to do that to us, so do it. All right, so anyway, on to the material of the course. So this course has to do with programming languages, and programming languages occur in many different contexts, not just as programs that you write in programming courses or that you deploy as software in the real world, but also it embeds itself, it emerges in strange ways. In the middle of a program, you might have to design a sort of a mini language whose very specialized to the project at hand. This kind of language design and language implementation thing happens all the time. It's sort of a valuable tool in your repertoire as a programmer. Now there are various strategies that we can use for actually implementing these things. We can, and you've encountered both of them during your time here. You can either take a program and write a program that will take whatever input language that you have designed or are targeting, and actually execute it according to whatever rules there are for that language. Or you can have a preprocessor kind of thing that goes through and converts, once and for all, converts the program into some more immediately executable form. Now actually, there are any number of, the modern trend as usual is moderation. So for example, you might have a compiler like the Java compiler that produces as its output another language, Java bytecode, which is not directly executable, but can be executed by an interpreter, the Java interpreter, which occasionally hauls off, since most modern Java interpreters are what are called just-in-time compilers, JITs, which occasionally hauls off and takes this bytecode and then translates it in turn, does more compilation, and converts it into machine code. So this is a sort of a hybrid approach, and it's rather common these days. We might be able to do a little bit of that even, or see something of both of these. All right, so let's do a little bit of history here, because this is sort of thing that faculty members, old faculty members, some of whom, like me, were around when some of these things actually happened. We like to justify our age and decrepitude by remembering them. Now, I wasn't around for the Jacquard loom or the analytical engine; those were back in the 19th century. But these are all examples of the first computers in which basically you program them by wiring them somehow or another. For example, for many years, there were these things called card sorters and accounting machines that basically would do some manipulation of Hollerith cards. Those are those rectangular things with the cut in the end. And these things had to be, you basically took out these plug boards with wires, and you rewired them to do whatever particular application you wanted. So then along came the stored program machines, and these, the idea here, the innovation here was that programs are data, something you learned in CS61A, and since they're data, you might as well have just one program, a sort of universal program in them that interprets this data as a program. And that very powerful thing made it much easier to change programs, and started basically was absolutely essential. You can imagine trying to do, say, Windows XP or Windows 7 with wiring, right? That's, what is it? Tens of millions of lines of code translated into wires. I can tell you that that's a lot of wire. And then, of course, you'd have to do it. Imagine what upgrades would look like. Yes, it would be a lot of fun. Now, it just wouldn't work. Now, then we started to see, excuse me, innovations in languages. So, fine, we've got this stored program computer. We put in a bunch of numbers that encode instructions, and it gets interpreted. Well, it gets interpreted by the hardware. Well, great, except that this is unreadable, basically. How do you program such a thing? So along came assembly language, which you've seen in CS61C, where basically this is a simple transliteration of numbers into something more readable, with an additional bit of bit of a symbolism, so that it's easier for you to remember and remember things, addresses and names and so forth, or instruction codes and so forth. So that's fine, okay. So that was sort of the way things were when I was born, actually, just to add a personal note to this. Fortunately, I was too young to have to suffer through this, and by the time I became aware that there actually were computers, along came John Backus and IBM to make an interesting innovation, which is to come up with this language that essentially gave you a virtual machine on top of the 701, made it look as if you have floating point registers and index registers, which that machine did not in fact have. It made things a lot faster, but it unfortunately made things run slower than native code. But, well, sometimes, since programming costs were soon seen to be a really big cost of using these things, maybe that wasn't such a bad thing. Maybe that wasn't such a bad trade-off. And then along came Fortran. Now, Fortran, it's hard to imagine what it was like at the time. I mean, people called this automatic programming. They thought it was they thought of it almost as a branch of artificial intelligence, because you would write down an algebraic formula, which looks nothing like what machine language is necessary to compute it, and this thing would translate it. Not only would it translate it, but it translated into, sometimes into code that was often better than what a rushed software engineer of the time would do, because, well, basically it was able to keep lots of details in its head, if you will, and take advantage of that. So this led to, at this point, there was a lot of research started into how to write compilers that were faster. And of course, Fortran is still around in its current form. Physicists say things like, I don't know what the language of the future will look like, but it will be called Fortran. Then you got this sort of Cambrian explosion of programming languages in the late 50s and 60s. First, it started sort of slowly. We got Lisp. Lisp is a language, Lisp of which Scheme is a dialect. It's a language that started in the late 50s. Its purpose was artificial intelligence. It basically arose out of the symbolic sort of processing of formulas and so forth that folks wanted to do in the wake of, to exploit or to explore artificial intelligence, because that's the way artificial intelligence looked in those days. These days, it's turned into a branch of applied probability and statistics, but in those days, it was much different. Now, Europe, of course, always averse to American dominance, has gone its own way in a number of ways. They came up with, largely Europe, they came up with Algol 60. They had American help, but a lot of European computer scientists worked on this. This is a nice language, and basically it's the syntax that, it's basically the syntax, or a form of the syntax that is familiar to all of us now. We'll see how different Fortran looks from modern syntax. And also, they had the first language description that was actually rather well done. I don't think, there haven't been as successful a language description, I think, since Algol 60. It was not only fairly complete, but more or less complete, but it was also readable. A crusty, famous computer scientist, the late Edsger Dijkstra, in fact called ALGOL a marked improvement on its successors, because basically its successors put in more and more bells and whistles, and ALGOL was nice and simple. And of course, the business community didn't want to be left behind. After all, International Business Machines, IBM, International Business Machines, it's time they wanted something a little better than Fortran, more suitable for their purposes, so along came COBOL. COBOL is a language that introduced, it was mostly the main source of modern records, structs, and that sort of thing that you find in programming languages these days. And then came a bigger explosion in the 60s. All kinds of people were exploiting all kinds of things. You had languages for dealing specifically with arrays, languages for strings, languages for formulas. Some of these, there isn't much. I don't know who does APL these days, although it's still around. Snowball is an interesting string processing language that has some implementations that are actually very fast, considerably faster than other things we use for string manipulation these days. Then object-oriented programming came along with Simula 67. No, it did not start with Smalltalk. It started with Simula 67. Now, if you ever see anyone say, Alan Kay invented object-oriented programming, you know whom not to trust for your future information. Okay. ALGOL 68. ALGOL 68 was one of these bells and whistles improvements, quote unquote, on ALGOL 60. I think it probably is what prompted Dijkstra to make his comment, because he was famously against ALGOL 68. Nevertheless, it was a very nice language. It was unfortunately crippled by the fact that a certain European by the name of Van Wijngaarden, who was perhaps too smart for his own good, very, very intelligent man, came up with a method of describing it that basically takes a year to master the method, that is. And then you can learn the language. It was he basically used a non-context-free grammar to produce an infinite grammar, and that infinite grammar was the grammar of ALGOL 68. Now you can imagine it's a little bit difficult to understand an infinite grammar, so people did not really understand this language too well. However, many of its interesting features you will still see remnants in languages like, for example, C. For example, the expression, the question mark colon is a different syntax, but really the same idea as ALGOL 68. And the method that C has for passing arguments is essentially the same one as in ALGOL 68. Everything is a value. Now, in 1968, there was this NATO summer conference about software, and it was announced that there was a software crisis. Software is hard to produce. It's buggy. It's unreliable, blah, blah, blah. Where have we heard this before? Or after, I should say. And this led to a bunch of languages that were attempted to be simpler and easier to formally verify. That is, easier to reason about. So we got things like the trend with simplicity, where we've got things like ALGOL W and Pascal. Then more emphasis on programming methodology, on methods, on programming language features that would allow you to design things properly, to isolate decisions in parts of the code, and thus make it easier to change things. A theme that we have occasionally harped on in 61A and 61B. So here you got various languages for supporting modular programming, that is, breaking programs into pieces that were isolated from each other, independent or largely independent of each other. You got experimental languages like CLU from MIT. Barbara Liskov was here last semester, I guess. She was the inventor of CLU. There was a language Modula. The Modula family came along. All of these languages were intended to, they didn't add any power, they didn't add any expressiveness so much as they did make it easier to design things cleanly. But there were other trends as well. There was this interesting language Prolog. This is a declarative language where instead of actually writing do this and then do that, you instead try to write the at least the ambition is that you write a description of the properties of the thing that you want to produce, and the program automatically does this. Well, not quite, but it was interesting. At the same time, these work on formally understanding programs, on the mathematics of programs, led to something called a project called the Language for Computable Functions, which I don't know if any remnants still remain today, except for this sort of side thing that they did, a meta language that they built in order to build reasoners about programs, called ML for meta language, and this became this is thriving community today of functional programming languages that came out of it, such as Haskell and OCaml. Now, the result of all of this explosion was that in the middle of the 70s, the DoD suddenly discovered that when you took all of its contractors and subcontractors into account, it was paying for the maintenance of something like 500 language dialects. 500 languages/dialects. So they said, okay, maybe this isn't good. I know that we're the DoD and we are famous for spending enormous amounts of money on toilet seats, but perhaps we could do a little better than this. And so they started a project that, first of all, cut down on the approved languages within DoD, and also led to the development of a programming language called Ada, that I had something to do with, actually, to sort of fill in any gaps in the languages that they had thrown out. So we see ever increasing, there's this sort of creeping featureitis that you see. So C++ became a more and more elaborate language, partially because they found the need for various features, partially because, as we will see, when you have a language like C++ that is statically typed, and you want to do all the object-oriented type of stuff, things can become a little complicated. But also because they were attempting to make things backward compatible with C. All of these have led to a good deal of complication in the language. So Java came along. That was largely the invention, I guess, initially of Jim Gosling, a fellow that I went to graduate school with. And this thing, and the idea here was to just basically throw away large parts of the complexity of C++. And start with do things from a cleaner perspective that's not necessarily backward compatible with C, although it does resemble it. Well, Java, of course, no one was satisfied with this, so they came out with new versions of Java. They got more complicated. They came out with, for one thing, Java had thrown away generic programming, which we'll talk about, and that turned out not to be so easy. C# comes along. Microsoft, as usual, goes its own way, and they did some interesting things, but they're different from Java, and they are more complicated. And then, very interesting, and sort of the thing that we'll be talking about, is this proliferation of lots of little languages for specialized purposes, many, but not all, are revolving around the web. So you have HTML, which is in effect a language, a sort of declarative language. PHP, which is an abomination, but is also a language that finds its use on the server side. Perl, which is another abomination, but is nevertheless very useful. Python, Ruby. The interesting thing about these languages is that as I say, they're not necessarily well designed as languages, but they carry with them these huge libraries of useful stuff, as a result of which the result is messy but kind of useful. So I'm going to get into a few examples, but at this point, why don't we take a few minutes break, because I'm sure that at this point you could probably stand to yawn at least. And we will restart in a couple of minutes. I prefer two or three. Necessary. Two is probably the best because there's always that chance that one will drop out.
When you say 2 to 3 partners, does that mean?
All right, I will clarify. All right, that's the second question I got. I meant groups of 2 to 4 yeah.
I just have a question about the pending status on enrollment.
Oh yes, that's all right. You're right. I forgot to address. I forgot to address that. Yes. Oh. Yes.
There's a case where if a product has to be done with 2 to 3 partners.
Yeah, I know. Everybody's been asking that question. I will answer it. All right. Could we start again, please? Oh dear, it seems I've been ambiguous about the project size. I would like my intention. I think the ideal size of a project in this course is probably 3, but I will allow 2 to 4. The problem with 2, of course, is that you know that some people will drop out in the middle of the semester, and I don't like doing this. It means we then have to find another home for the remaining partner. Of course, there will also be cases where 2 people drop out, which is also problematic, but you can't have everything. So nominally, so sort of shoot for 3, and if necessary, we can accommodate 2 to 4. Remember that with more partners, there's a bigger problem with splitting the work up properly. Now, the other thing has to do with enrollment in this course. Now, as you know, there are 2 new sections that were added late. I'd like to ask everybody those who are both on the wait list and not on the wait list, if you're on the wait list, you have to get into one of these sections that's not full. Just sign up for it. And in order to get off the wait list. And the other thing is that those of you who are in the course, please reconsider your discussion section choices now that you have 2 more choices. And if necessary, go into Telebears and change your section. We'd like you to do that so as to make things more available. So I think it tells you how many people are in each section. The first 2 sections, whatever it is, 101 and 102, those are full at the moment. But if people would just move around a bit, I think we can probably accommodate everybody, because there are enough lecture seats for the size of the waiting list. So please do this. those of you who are trying to enroll concurrently, I will probably not know until I'll probably do that early next week. Okay. So any other questions I can handle afterwards. All right, let me go back to a quick look at some examples. This is good old Fortran from way back. This is an old style Fortran. You'll see some of the interesting little features here. For example, as you can see, you notice that that the types are missing from these things. We don't say that these are real or integers. They aren't actually missing. They are implicit. All the variables that start with the letters I through N are integers, and all the variables that start with other letters are real, except for those that appear in a dimension statement, which are in fact arrays. Okay? Very simple. And notice the interesting form of the if statement. So if n minus 1, 40, 40, 10, that means if n minus 1 is less than 0, go to 40. If it is equal to 0, go to 40. And if it is greater than 0, go to 10, where 10, 40, and so forth are labels. Got a hole in my pocket here. Are labels on the statements to follow. So that's kind of funky. Not only that, but these statement labels must appear in columns 1 through 5. So this is column sensitive. Columns 72 through 80 are reserved for a card sequence number. They are ignored, but you can put in a sequence number so that, this is ridiculous. I've got to be, you can put in a card sequence number so that your card sorter can help you if you drop your deck on the ground. Great stuff. I just love this. All right. Then you have the loop statement, do 30I equals 2 comma n. Now I've indented this to show it that was not, in fact, standard practice. Everything was up against column 7 margin there. I should say that to continue a line, you put a character in column 6. What is with this? You know, this security can go too far, right? This is a perfect example. You put a little continuation character in column 6, and that would indicate that your line was a continuation. Oh, it's great. And these do loops, do 30 means that 30 is the end of the loop, and I equals 2 comma n. That means that the loop variable goes from 2 to n. Obviously, that's not too surprising. And comments start with a C and go to the end of the line. Input and output is kind of interesting. You have a separate format statement that gives you the format of the input, and then you refer to that format in your read statement. And you'll notice read 5, write 6. 5 and 6 are channels. They refer, instead of saying from the standard input to the standard output, you say 5 and 6. Perfectly natural, of course. Well, that was very interesting. That was sort of our first attempt. Then along came Algol 60. This looks a lot more reasonable. This looks like old C, actually. So you see the parameters are listed after sort, and then their types are given afterwards. And this was Algol. I think you can probably figure out, probably by looking at this, what it means. It wasn't too particularly surprising. Then along came APL. Now APL, this is much simpler because APL was an array-oriented language. So if you want to sort something, you just say, okay, give me, sort the array A, I just take this operator, triangle with a bar through it. By the way, you couldn't use an ordinary, you had to have your own special input device to put things into APL, so they had all kinds of strange conventions for these things. They had Greek letters. Oh, it's really quite a character set, I have to say. So that particular operator there means the indices of the elements of A in sorted order. So that is, and then you apply that that gives you a vector of integers, and you apply it to the array, and that gives you a vector of elements of selections out of the array. All very neat. Python, this one, unlike the APL example, is kind of a cheat because it doesn't do any input and output. This does all the input and output. The sorting is right here, right here where you see the vals.sort. That's sorting because it's a built-in thing. As I said, these new languages, they have big libraries, and this is an example of them. And to read in everything on the input, we just use this map. You've seen that before. Yes, this is map from CS61A. Float is something that converts strings or anything into floating point numbers. And this little thing here is just something that says read all of the input, strip it, split it up at all the white space, and then giving me an array of strings, which I then map float over, giving me an array of floats, which I then sort. And then down here is this print thing, which basically says, and you can go to the Python documentation and understand how it says it, but it basically says take the resulting values in groups of 6 and print them out each on a line using this format up here. So that you could do that. It's very nice. And if I hadn't cared about the output format, I would have just said print vals instead and eliminated a lot of that, and I just get a list of all the values. Prolog, oh, this is kind of an interesting thing. This is an example of how you would never want to do this, but it's the wonderful academic example of how Prolog works. So basically in Prolog, what you have, and we'll actually be doing some exercises with Prolog. What you do is each one of these things, ordered, sorted, and permutation, is a relation, not a function. It's a relation. That is, you can think of it as being true if its arguments stand in a certain relation to each other. And we define all of these relations, or predicates, actually, by saying, by defining a relation or a predicate called permutation, which says that its first argument is a permutation of its second argument. And then we define something else called ordered, which is true if the elements of the list that you give it are in order. And then you just say something is sorted if it's a permutation, or B is a sorted version of A, if B is a permutation of A and B is ordered. Well, obviously, all of these things together, that's what sorted means. So if you put this together and give a list, if you say permutation of, give a list and then question of, and then a variable, the thing will say, well, that variable must equal blah, which will be the sorted value of the list. You can put it in backwards. Say, what lists give me this as a sorted value? And it will give you all the possible permutations of that list. It's kind of neat. So what are we going to have to do? Okay, so those are some examples of programming languages. So what are the problems that we're going to have to be solving over the course of this semester? Well, first of all, we have to figure out a way of describing the language, describing languages so that programmers can understand them, implementers can understand them, and preferably so that implementers can possibly automatically produce implementations or complete or partial implementations for the programming languages. How are we going to test these things? What are the procedures that one uses to test that you have a proper implementation of a programming language? What are the shortcuts? I mean, there's a lot of tedious work here. What can we do to cut that down? What sort of standard things do you do with every program translation that can be somehow wrapped up and bundled once and for all as a tool? And how do we do? There are various things about making languages useful, like how do you handle errors? How do you compile quickly? What do you do about questionable constructs? How do you detect probable errors in programs that are technically legal? And this leads the classical structure that we will be starting from anyway looks like this. You have a source program. You turn it into a stream. You break it down into a stream of atoms, if you will, tokens, individual pieces. Thus throwing away a piece of detail, like the white space between things. We call that lexical analysis. You then take this stream of tokens and we parse it into something that you've seen in 61A, namely a tree, an abstract syntax tree of expression tree or something like that. We perform some analysis on this that tells us, that answers such questions as, here's a declaration, what other variables in the program does this declaration control? We generate code from it, such as, for example, virtual machine code, something like that. This can then be optimized, that is to say, optimized means improved into something better, and then eventually the whole thing becomes optimized machine language, or possibly goes off, at some point, goes off to be interpreted. So that basically is, in a nutshell, the sorts of things that we will be doing in the course of this semester, the kind of thing that this project that we'll be doing does, and sort of an idea of the subject matter, of the history at least of the subject matter of this course, the programming languages themselves. So I think it can be a lot of fun. Just as I say, just remember my advice: start early. All right, thank you.